In this video, we're going to practice integrating partial fraction decompositions. So we're going to start with some relatively easy ones, and then we'll work up to some more challenging examples. So basically, what's happening here is that perhaps you're given an integral like we see over to the left here. The integral of 4x minus 7 over x minus 3 times x plus 2. Now, there's not really a good way to solve this integral or to evaluate this integral until you use the process of partial fraction decomposition. So I'm not going to show that here. We've looked at that in previous videos and previous examples. But let's say that you do the partial fraction decomposition on this expression, and that leads you to this new expression over here, where we have the sum of these two more simple rational functions. So now I have the integral of 1 over x minus 3 plus 3 over x plus 2, and now I need to integrate this expression to finish the problem. Well, luckily these are pretty simple expressions, and that's why partial fraction decomposition is so helpful. It can take something more challenging and give us the sum of more simple expressions that we can actually integrate. Now in this case, these are both just natural log forms. So if it's helpful, you can think about separating this integral into two separate integrals. And then for each of these, you might not need to do this, but if you do, you can just make a simple u substitution. For example, here I might let u equal x minus 3. So then du would be dx, and I'd end up with the integral of 1 over u du, which is the natural log of the absolute value of u. And if I substitute back in my u, I get the natural log of the absolute value of x minus 3. And we could do the same thing for this other integral here. And we end up with another natural log expression. So then this expression here would be our final answer in this case. In this example, we're given the integral of this kind of nasty looking rational function on the left here. And we looked at this rational function previously in this lesson, and we found the partial fraction decomposition shown on the right here. And if you recall, what we had to do is we actually had to use long division first on this expression, since it's improper, and then we were able to use partial fraction decomposition. And that's why we have this polynomial term right here, this 2x plus 1. Let's go from what we already have, this partial fraction decomposition, and actually finish out the problem and integrate this. So if it's helpful for you, you can split this up into different pieces to help you think about how to integrate each term. So our first few terms here are pretty straightforward. So the antiderivative of 2x is just x squared. And then I have the antiderivative of 1, which should just be x, so plus x. And then here I have 5 over x, so that should give me 5 natural log of the absolute value of x. And then I get into ones that are slightly more challenging, but still not very difficult at all. If it's helpful for you, you can do a u substitution. And actually we could use the same substitution on both of these, right? Because they both have this x minus 1 expression in the denominator. So let's let u equal x minus 1. In which case du would equal dx. So then I end up with the integrals 1 over u du plus 3 times the integral. This is going to be 1 over u squared, so I'm going to write it as u to the negative 2 du. So this integral of 1 over u du, of course, is going to give us the natural log of the absolute value of u. And then plus, here I'm going to have 3u to the negative 1 over negative 1. We can add our plus c in the end here. So that's going to give me the natural log of the absolute value of u. And let's see, we'll write this as negative 3 over u plus c. And then finally we want to substitute back in our expression for u. So that should be the natural log of the absolute value of x minus 1 minus 3 over x minus 1 plus c. So then if I put all my pieces together, I find that this original integral is equal to x squared plus x plus 5 natural log of the absolute value of x minus the natural log of the absolute value of x minus 1 minus 3 over x minus 1 plus c. So let's say we were presented with the integral shown on the left here. The integral of x cubed minus 5x squared minus x minus 3 all over x to the fourth minus 1. So to approach this integral, a method we would probably want to use is partial fraction decomposition. Right now there's really no other way to evaluate this integral. But if we use partial fractions, then we're able to break it down into some simpler pieces, and then we can integrate those simpler pieces. So let's look at the process of after we've used partial fractions, how we would integrate the result. So I can break this integral up into 3 different integrals, if that's helpful. And really the most challenging of these 3 integrals is this first one. The second 2 are just natural log forms. So in this first integral, what's probably going to be the most helpful way to approach this is to actually split up this fraction into 2 pieces. Okay, so I'm going to further split up this first term into x over x squared plus 1 dx minus the integral of 1 over x squared plus 1 dx. And then I can carry down these other integrals as well. All right, so let's start with this first integral here. I have the integral of x over x squared plus 1. This looks like a candidate for just a basic u substitution. So I'm going to let u equal x squared plus 1, which means then du is 2x dx, or 1/2 du equals x dx. So then if I rewrite that integral, I'm going to have a 1/2 out front, and then I'm going to have 1 over u du. Okay, so that just gives me 1/2 times the natural log of the absolute value of u. We'll add in our plus c at the very end of everything. So then substituting my u back in, 1/2 of the natural log of x squared plus 1. I dropped the absolute value symbols since x squared plus 1 is always positive. So now let's proceed to our second integral. Hopefully you recognize the form of this integral. This is actually the inverse tangent or the arctangent form. So you can recall, hopefully, that the integral of 1 over x squared plus a squared, where a represents a constant, equals 1 over a inverse tangent of x over a plus c. And that's the form we have here. Here our a value is just 1. So then we can just write down the answer for the second integral. So I'm going to have minus 1 over a, but that's just 1 over 1. So inverse tangent of x, and that's it. So now we come to the integral of 2 over x plus 1 dx. A lot of you may be able to just write down the answer to this at this point, but just to be sure we understand, we can do a simple u substitution if needed. We can just let u equal x plus 1. So then we'll have du equals dx. And this will become the integral of 2 over u du, which would give us 2 times the natural log of the absolute value of u, or 2 times the natural log of the absolute value of x plus 1. And then we come to this last integral, which really is pretty much exactly the same as the one we just did. We just have x minus 1 on the bottom. So you could do a u substitution if you need it there, But what you're going to get if you do that is 2 times the natural log of the absolute value of x minus 1. And we're subtracting that. And then we'll just add a plus c on the end of everything. So this here, this long expression, is the antiderivative of this original nasty looking rational function, and we were able to find this because we were able to do this partial fraction decomposition. So far, all the integrals that we've looked at have been relatively simple. We haven't had to do anything too crazy to solve them. So now let's take a look at probably one of the most challenging type of integrals you could get from a partial fraction decomposition. So here we're not looking at the original expression this came from. This is just one possible term in a partial fraction decomposition. And what makes this more challenging is I have this quadratic in the denominator that's being raised to, in this case, the third power. So how are we going to approach this? Well, maybe your first instinct would be to try a u substitution, and that's always a great thing to try. So in this case, if I let u equal this denominator, x squared minus 4x plus 13, I would get that du equals, let's see, 2x minus 4 dx. But that doesn't look like it's going to work out all that well for us because I have a 4x minus 1 in the top, and I don't really see any good way to get from 4x minus 1 to 2x minus 4. So it looks like maybe we need to think a little bit more here. Now I have this quadratic expression in the denominator here. Often when you have a quadratic expression, completing the square can be helpful. So let's try that. Let's try rewriting x squared minus 4x plus 13 by completing the square. So we'll just work on this out to the side for a second. So if you recall, when we complete the square, what we're going to do is we're going to be adding some special number in here. So I'm going to insert a blank where I'm going to add some constant, but in order to not actually change the expression, I'm going to subtract that same value, whatever it may be. Now the way we find that special number is we look at this coefficient of the x term, which in my case is -4. We take that coefficient and we divide it by 2 and then square the result. Okay, so here that's going to give me -2 squared, which is 4. So 4 is my special number, so I'm going to add 4, and then I'm going to subtract 4 as well so that I don't change anything. Now what I want to do is I want to group these first 3 terms together. So this x squared minus 4x plus 4 is what I'm particularly interested in. And then it looks like out here I'm going to have a plus 9. So if I did this correctly, this new quadratic here should be what we call a perfect square. So if I look at this, I can factor this into x minus 2 times x minus 2. So then this becomes x minus 2 quantity squared plus 9, and that's why it's called completing the square, right? We're trying to get something squared here. So using this, let's come back here and rewrite our integral. Okay, so now things are going to get maybe a little bit strange, but what might be helpful here is if I could get this to the form u squared plus 9 in the denominator. Instead of this x minus 2 quantity squared. U squared plus 9 in the denominator is something that we've dealt with in the past. So then let's try u substitution and see if it's helpful. Let's just try letting u equal x minus 2. Okay, so that's going to give me du equals dx. That part's pretty straightforward. But then notice on the top here, I'm going to need something to substitute for this 4x minus 1, right? I need to get everything in terms of u. So if u equals x minus 2, then I can say that x equals u plus 2. So let's try rewriting this integral using all of these substitutions. So on the top then, I'm going to get 4, and this x I'm going to write as u plus 2, and then I have minus 1. On the bottom, I'm going to get u squared plus 9, all of that raised to the third power, and then dx is just du. So expanding on the top there, I get 4u, and then I'm going to have plus 8 minus 1. So I'm going to go ahead and write that as plus 7. And then on the bottom, I've got u squared plus 9 quantity cubed du. This looks a little better, right? It looks a little simpler. Let's actually split this up into 4u over u squared plus 9 quantity cubed du plus 7 over u squared plus 9 quantity cubed du. Now we'll think about each of these integrals separately. Each is going to require a slightly different approach. We'll start with this first integral. This one's actually not too bad. So notice I have a u squared plus 9, right? So u to the second power in the denominator, and I have this 4u in the top. So maybe just a u substitution would work to solve this problem. So let's use w and say w equals u squared plus 9. So then dw is going to be 2u du. Or I could say that 1/2 dw equals u du. So then going back and rewriting my original integral, I'm going to go ahead and pull this factor of 4 out front, and I'm going to combine it with this factor of 1/2 that I know I have to introduce. So I'm going to have a 4 over 2 out front, and then my u du on the top is, of course, 1/2 dw. I already have the 1/2 out front, so I'm just going to get a dw there. And on the bottom, I have u squared plus 9. Oh, well, that's just w, so w cubed. Well, that's not so bad. So this is the integral, or 2 times the integral of w to the negative 3 dw, and we can solve that. So that's 2 w to the negative 2 over negative 2. I'm going to leave off the plus c for now, and we'll just add it in at the very end. So it looks like then I get negative 1 over w squared. So negative 1 over the quantity u squared plus 9 squared. Well, let's look at this second integral now. This is perhaps going to be a little bit more challenging. Now to do this integral, we actually need to remember the technique we just learned in the last lesson. So what's going on here? Well, in the denominator, I have this u squared plus 9. Now, just by itself, that kind of looks like an inverse tangent form, but the fact that it's raised to the third power messes us up. So we're going to need to use some sort of different technique. And actually, the technique that's going to work here is the technique of trig substitution. Okay, so remember what we said about our trig substitution forms. If we have something of the form a squared plus u squared, where a just represents a constant, we said that the substitution u equals a tangent of theta would be helpful. And here that's exactly what we have. It's addition, so it's okay that it's written in a different order. We can think of this as 9 plus u squared. Okay, so then let's make a substitution. So in my case, because my a is 3, right, 9 is 3 squared, I can say let u equal 3 tangent of theta. So then in that case, du is going to be 3 secant squared of theta d theta. So our integral is going to become the following. I'm going to pull the 7 out front for a while. Okay, we said our du was 3 secant squared of theta d theta. And on the bottom, I have u squared plus 9. So that should be, if I square my u, which is up here, 3 tangent of theta, that would be 9 tangent squared of theta plus 9, and that whole quantity is cubed. Now typically what we do next in these trig substitution integrals is we use a Pythagorean identity to reduce or rewrite something. So this 9 tangent squared of theta plus 9, if I factor out a 9, I've just got 9 times tangent squared of theta plus 1, and tangent squared of theta plus 1 is equivalent to secant squared of theta. So then my integral becomes 7 times 3 secant squared of theta over 9 secant squared of theta, quantity cubed, d theta. So let's reduce this a little bit. I can combine the 7 and 3 and get a 21 out front. And then notice in the denominator I have this 9 cubed, which is 729. I'm going to pull that out front. And then inside I have still a secant squared of theta on top. On the bottom here, if I cube secant squared of theta, I'm going to have secant to the 6th of theta d theta. So this gives me 21 over 729 times the integral of 1 over secant to the 4th of theta d theta. Now remember that 1 over secant is the cosine, so I can write this as 21 over 729 times the integral of cosine to the 4th of theta d theta. Now even though this integral here looks relatively simple, there's still actually a good bit of work to be done. So what I'm going to do is I'm just going to summarize the next few steps so we don't spend too much time on these gritty little details. So the first thing I'm going to have to do here is write this as cosine squared of theta times cosine squared of theta d theta, and then replace each of those cosine squared of thetas with the appropriate formula using the half-angle trig identities. And then I'll expand this expression by foiling. Then I'm going to have to use a half-angle formula again on this cosine squared of 2 theta term. And I also added in a few lines of simplification to get to this point here. And now I can go ahead and integrate this in terms of theta and get the following. I'm going to leave off the plus c for now, and we'll add in a constant of integration at the end when we're done with all our integration problems. Now the next thing I'm going to have to do is get my thetas back in terms of u. Now to do that, instead of having sine of 2 theta and sine of 4 theta, I'm just going to want to have sine of theta. So I'm going to have to use the same formula to do that. Sine of 2 theta equals 2 sine of theta cosine of theta. And it looks like I'll also need a power or a double angle formula for cosine. So cosine of 2 theta equals cosine squared of theta minus sine squared of theta. So now I have everything in terms of theta, sine of theta, and cosine of theta. But I need to use my original trig substitution to figure out what those things are in terms of my original variable u. So my original substitution was u equals 3 tangent of theta, or u over 3 equals tangent of theta. So know that theta equals the inverse tangent of u over 3. Right, that takes care of this theta. I can solve for sine of theta and cosine of theta by setting up a triangle. So we get the following. Remember, you can pause the video at any time if you want to examine any of these steps in more detail. So I'm going to substitute these expressions back into my last line in blue here. So now that we have everything back in terms of u, we've actually finished evaluating this second integral here. So I've pulled that down here and then finally added in our plus c. Now this u represents something else, right? We had made a substitution in the beginning. So instead of writing that all out though, we'll just say where u equals x minus 2. And this here then is the answer to our original integral that we started with. Now this was super painful and tedious, and this is much harder than anything that you would expect to see on an exam. So the point here to take away then is that you really need to be familiar with all these different integration techniques that we learned, and practice enough so that you're able to apply them when necessary. Right? So to solve this integral, we had to use several different integration techniques that we've learned in the past.